This is section 7 of our tutorial. The section title is Full Band Extensions. In previous sections, we treated underdetermined BSS methods such as R1CA, FCA, and FastFCA. In this section, we introduce full band extensions of these methods, namely rank 1 MNMF, full rank MNMF, and FastMNMF. In section 3, we saw how time-varying Gaussian ICA for narrowband processing can be extended to ILRMA for full-band processing by incorporating NMF as a source model. Here, as explained earlier, in narrowband processing, each frequency component is processed independently, whereas in full-band processing, all frequency components are processed jointly. In this section, we do very much the same thing in the context of underdetermined BSS. That is, narrowband method for underdetermined BSS, such as R1CA, FCA, and FastFCA, are extended to full-band BSS method based on NMF. This section is structured as follows. First, we extend R1CA to rank 1 MNMF. Then we extend FCA to full rank MNMF. Finally, we extend FastFCA to FastMNMF. So now we talk about extending R1CA to rank 1 MNMF. In both R1CA and rank 1 MNMF, the log likelihood to be maximized is given by this equation using the mixing vector A. We make the frequency bin index I explicit in this section because all frequency components are processed jointly. The log likelihood can also be expressed as in this equation using the mixing matrix. The difference between these methods lies in how the source power spectrum H is parameterized. In R1CA, it is a free parameter, whereas in rank 1 MNMF, it is parameterized by NMF. In rank 1 MNMF, the mixtures X are modeled by this equation as in R1CA. Each source signal is modeled as in Itakura Saito NMF. That is, each source signal is modeled by the sum of k components denoted by S tilde, as in this equation. We call S tilde a subsource component. We assume that the subsource components independently follow complex Gaussian distributions shown here. The noise is modeled by complex Gaussian distribution shown here, as in R1CA. By using this model, the distribution of the mixtures is given as shown here. as in the previous slide. This slide summarizes different expressions of the signal model in rank 1 MNMF, which are all equivalent. As in R1CA, the signal model is expressed like this, using the Maxim vectors, or like this, using the Maxim matrix. We can also rewrite it by using the subsource components like this. This can also be rewritten in matrix form here, where A tilde and S tilde are defined by these equations. An EM algorithm can be derived in a similar way as in R1CA, where a difference lies in that the latent variable Z consists of the subsource components instead of the source signals. The E step updates posterior distribution given by this equation, where we need the prior distribution shown in blue and the likelihood shown in orange. The prior distribution decomposes as shown here on the assumption of sample independence and independence of the subsource components. By using this model, the prior distribution can be rewritten like this. As for the likelihood, it also decomposes like this, and by using these equations, it can be rewritten like this. Consequently, although we omit the details, the posterior distribution turns out to be a Gaussian distribution shown here, where the mean mu and the covariance matrix sigma are given as in these equations. Although we omit the derivation, the Q function is given by this equation. Here, the blue variables are the parameters of the joint posterior of all subsource components S tilde. After some calculations, this can be rewritten like this. Here, the red variables are the parameters of the marginal posterior of each subsource component S tilde. The green ones are those of the joint posterior of all sources S. In the E step, it is therefore sufficient to update red and green variables instead of the blue ones, which is computationally much more efficient. Parameter update rules are obtained by partial differentiation of this Q function. This is the pseudocode of the EM algorithm for rank 1 MNMF. Now we talk about extending FCA to full rank MNMF. The key to extending FCA to full-rank MNMF is to incorporate NMF as a source model in a very much the same manner as before. In both methods, the log likelihood to be maximized is given by this equation. The difference between these methods lies in how H is parameterized. In FCA, it is a free parameter, whereas in full-rank MNMF, it is parameterized by NMF, as shown here. Our latent variables consist of what we call subsource components, denoted by C tilde. We assume that each source image C is modeled by the sum of k subsource components C tilde. We also assume that these subsource components independently follow complex Gaussian distributions shown in this equation. Consequently, the mixtures X are modeled by the sum of C tilde over all n and k, and follow the complex Gaussian distribution given by this equation, corresponding to the log likelihood given in the previous slide. The set of latent variables Z is defined by this equation, where the last subsource is excluded as in FCA. Although we omit the derivation, the posterior distribution to be computed in the E step turns out to be a Gaussian distribution. And the mean mu and the covariance matrix sigma are defined as in these equations. Although we omit the derivation, the Q function is given by this equation. Here, the blue variables are the parameters of the joint posterior of all but the last subsource components. After some calculations, this can be rewritten like this. Here, the red variables are the parameters of the marginal posterior of each subsource component C tilde. In the E step, it is therefore sufficient to update the red instead of the blue variables, which is computationally much more efficient. Parameter update rules are obtained by partial differentiation of this Q function. This is a pseudocode of the EM algorithm for full-rank MNMF. Now we apply the MM algorithm to full-rank MNMF. Our cost function is the negative log likelihood given by this equation. As in FCA, the red and the blue parts are difficult parts to handle, and so we aim to majorize them by functions that are easier to handle. To this end, we can use these two inequalities as in FCA. Consequently, we obtain an auxiliary function shown here that majorizes the cost function. The auxiliary variables psi consist of gammas and pi's. Although we are not going into details in very much the same way as before, update rules for the auxiliary variables are obtained by the equality conditions and those for the parameters by partial differentiation. This is a pseudocode of the algorithm for full-rank MNMF. Now we talk about extending FastFCA to FastMNMF. To extend FastFCA to FastMNMF, we incorporate NMF as before. In both FastFCA and FastMNMF, the log likelihood to be maximized is given by this equation. The difference between these methods lies in how H is parameterized. In FastFCA, it is a free parameter, whereas in FastMNMF, it is parameterized by NMF like this. Our objective is maximizing the log likelihood, which is equivalent to minimizing the negative log likelihood given by this equation, as in FastFCA. Unlike FastFCA, here H is parameterized by an NMF model. Here, the blue part can be regarded as a cost of time-varying Gaussian ICA relevant to updating W. On the other hand, the green part can be regarded as a cost of tensor decomposition based on the Itakura-Saito divergence, which is relevant to updating lambda, d, and v. Consequently, we can optimize the cost efficiently by alternately applying ICA updates for W and tensor decomposition update for lambda, t, and v. For example, W can be updated by iterative projection, IP, and the other parameters by MM, which can be derived in the same manner as in FCA. We skip the derivation because it's almost the same as before. This is a pseudocode of an IP plus MM algorithm for FastMNMF. This is section 8 of our tutorial. The section title is The Three Constraints. As I alluded to in section 1, the three axes of the cube represent three constraints on model parameters. In this section, I reveal what these constraints exactly are. Importantly, in all Bss methods explained in this tutorial, the log likelihood to be maximized has the same functional form shown here. Here, let me remind you that R denotes the spatial covariance matrix, H, the source power spectrum. B, the noise covariance matrix used in R1CA and rank 1 MNMF. And theta, the set of model parameters. The difference between Bss methods lies in the parameterization of R and H. In FCA, both R and H are free parameters. In R1CA, R is a rank 1 matrix parameterized by the mixing vector A. In FastFCA, the spatial covariance matrices R of all sources are jointly diagonalizable and so parameterized like this. As for time-varying Gaussian ICA, although this may not be obvious, R is parameterized like this. I will show this in the next slide. Once this is shown, it is clear that the full-bound methods correspond to the parameterization shown here, with H parameterized by using NMF. Now we derive the parameterization of the model parameters in time-varying Gaussian ICA in the previous slide. Please recall that in time-varying Gaussian ICA, we make the following assumptions. The first one is linear transform. The separated signal Y equals the mixtures X transformed by the separation matrix. The second one is output independence. The separated signals Y are independent as shown in this equation. The third one is the time-varying Gaussian distribution. Each separated signal is modeled by the time-varying Gaussian distribution. By using this model, we can derive the parameterization. By the second and the third assumptions, the joint distribution of the separated signals Y is given by this complex Gaussian distribution. Here, H is the diagonal matrix defined as shown here. The distribution can be rewritten like this, where En denotes the nth column of the identity matrix. Therefore, from the first assumption, the distribution of mixtures X is given by this equation. Here, the red part corresponds to the spatial covariance matrix R. So we have shown the parameterization in the previous slide. Moreover, the difference between methods can be explained by whether or not three constraints are imposed on model parameters. These constraints are the joint diagonalizability constraint on R, the rank 1 constraint on R, and the NMF constraint on H. These three constraints are represented by the three axes. In FCA, both R and H are free parameters, or in other words, no constraint is imposed. That's why FCA is located here at the origin of the coordinate system. In R and CA, the rank 1 constraint is imposed on R, and so R1CA is located here. In FastFCA, the joint diagonalizability constraint is imposed on R, which is why it is located here. As for time-varying Gaussian ICA, it may not seem obvious why it is located here, but we explain this in the next slide. As for the other four methods, it is obvious that they should be located here. This slide summarizes what we can show about time-varying Gaussian ICA. Although derivation is omitted here, it is to be included in a journal paper in preparation. We assume that both the rank 1 and the joint diagonalizability JD constraints are imposed on R, along with certain mild conditions. Then we can show that R can be written like this, which is nothing but the parameterization in time-varying Gaussian ICA. We can also show that the number of sources, N, should be equal to the number of microphones, M. That is, the determined condition is an immediate linear algebraic consequence of the simultaneous presence of both constraints. Moreover, we can show that the multi-channel Wiener filter reduces to the separation matrix followed by projection back. Various properties of Bss method can be explained by using this cube. As I explained in the previous slide, when both the rank 1 and the JD constraints are imposed on R, the determined condition is automatically derived. This implies that underdetermined BSS is possible when either the rank 1 constraint or the JD constraint is absent, which corresponds to the region shown in blue. Moreover, computationally efficient BSS is possible when the JD constraint is present, which corresponds to the region shown in orange. These properties highlight the advantage of FastFCA and FastMNMF over the other methods. Time-varying Gaussian ICA, located here, is efficient because of the JD constraint, but incapable for underdetermined BSS because of the simultaneous presence of the rank 1 constraint and the JD constraint. On the other hand, R1CA and FCA, located here, are capable for underdetermined BSS by removing the JD constraint, but this is at the cost of efficiency. In contrast, FastFCA, located here, is not only capable for underdetermined BSS, but also efficient by removing the rank 1 constraint but retaining the JD constraint. Similar statements hold for the full-band extensions located here. Here, an interesting question arises. Is it possible to make R1CA or rank 1 MNMF faster based on the JD constraint, just as FCA or full-rank MNMF are made faster based on it? The answer is yes. It is nothing but time-varying Gaussian ICA or ILRMA. We can consider time-varying Gaussian ICA to be fast R1CA and ILRMA to be fast rank 1 MNMF. However, these methods are limited to the determined case, unlike FastFCA or FastMNMF, because of the simultaneous presence of both the rank 1 and the JD constraints. Furthermore, permutation-free BSS is possible when the NMF constraint is present, which corresponds to the region shown in purple. So, I'd advocate that FastMNMF is a very nice method, capable of underdetermined BSS, computationally efficient, and permutation-free. Now we conclude this tutorial. In this tutorial, we presented a unified framework for underdetermined and determined blind audio source separation. The framework is represented by a cube, as in this figure, where the 8 vertices represent BSS method and the 3 axes the 3 constraints on model parameters. The framework enables us to garner a unified understanding of the BSS methods. Especially, it elucidates close relation between underdetermined and determined BSS that have been studied somewhat independently of each other, hopefully creating synergy between these research areas and stimulating further advances of them. Thank you. These are the selected references. This is the complete list of the references.